Hello, CJ.
Hello?
Okay, hold on. I haven't turned on my camera yet. There we go.
Hello?
Hello?
Is my mic working?
Yeah, I can hear you, but do you hear me?
Hello? I
Okay,
can't hear you.
okay, hold on.
Hello?
Okay, can you hear me?
Yes.
All right, there. All right, so what are we doing today? How are you, by the way?
Oh, the mic changed again.
Okay, hold on.
It like cut off.
That's strange. It's doing its off the volume thing again. Hold on. How about now?
Oh, it's good. Wait, why can't I
Okay.
write as well? Oh, okay.
Uh, okay. This isn't actually the jam board yet. This is the board from Preply.
With the mic keeps like going up and then down. Like,
Yeah, yeah, I got it. That's really strange. Hold on, let me do that one more time. Hmm. All right, how about let's see. Let's see what it
okay, now it's
does.
good.
Okay, good. Um, okay. So what are we doing
Oh,
today?
I have a electricity summative on Wednesday.
Wednesday. Oh, we'll continue electricity then, right? Uh, okay. Hold on. Where is that thing? Okay, I'm gonna have to look for that setting again because I was able to turn it off before, but now it's my microphone just keeps resetting itself for some reason.
Oh,
Okay, but I can manage. I can manually change it every time.
hmm.
Every time it happens. Other thing I can do is I can get the mic a little bit away from me. Let's see how that works. All right. Okay, so we'll just continue what we were doing before, which was electricity and magnetism. Okay, there we go. Okay, this is okay. Let's do that one more time. I can write on the tablet. So anyway, yes, last time I think we did circuits, right? I can check the Jamboard from last time to
Yeah.
see. I guess what we can do now is internal resistance. I think we still kind of did internal resistance, right? And we'll go to Kirchhoff's rules. Okay, so this is CJ. Okay, here's the link to the board. Okay. Um. Okay. So again, so for today we're doing internal resistance and internal resistance and Kirchhoff's rules. Okay. Uh. Okay. So let's start off with internal resistance. Let's do a quick recap of the concepts. Okay. So the first one again, internal resistance is part of the battery or cell. Okay. So internal resistance. Okay, it's part of the battery or cell. And then one thing that you would know here is if you have a graph and the graph looks like this, then this is something like this. Let's say this is a VI graph, sorry, IV graph. Okay, VI graph like this. Um, this would be your the EMF of cell. Okay, and then the slope would be equal to um, internal resistance. Okay, so keep this in mind. This is going to be important here. Yep. Oh, hold on. Yeah, thank you. Seriously? Okay, let's do that again. Oh, probably it's because I haven't shared it yet. Hold on. Ah, okay, there we go. Try again, try again. Works now. All right. Okay. So now that it works, let's also share that here on the screen. Okay. Um, okay, so again, so that's it, the internal resistance in Kirchhoff's rules. For internal resistance, it's part of the battery like that. And then the EMF of the cell is going to be the y-intercept on the VI graph. And then the slope of that graph is the internal resistance. Okay. The rest of it, it's basically you follow the rest is basically Ohm's law. Okay. All right. So do you have any questions that were given to you, or should I provide the questions today? Oh, you don't have. All right. So I'll just get a few questions here. Give me a few moments. Where is it? Mhm. Let's do a paper two. Okay. Let me go there while the paper's loading. Okay. This is the idea. Okay. So when you have a circuit like this, and it has an internal resistance like this, right? Okay. So something like that, and there's gonna be a current flowing through here, right? Right. And then this is big R. This is small r, the internal resistance. Um, and then let's say that this, if you put the voltmeter across here, if you put the voltmeter across there, okay, the voltage would be equal, if you use Ohm's law, it will be equal to I times big R plus small r, right? Actually, no, let's not put that there. I'm not gonna put that V there. Okay, so what I'm gonna do instead is I'm gonna place that somehow, if we can do it. Now, in reality, we can't do this. There's your V. Let's not even label that V. Let's label that EMF, right? It's the EMF, right? So the EMF here will be equal to this. This is just Ohm's law, right? So if I'm gonna expand that, that's gonna be EMF is equal to IR plus I small r, right? However, if you think about it this way, if I'm going to attach, I'm going to use blue this time. If I'm going to attach an actual voltmeter, I can only do that there, outside the internal resistance, right? So this is basically connected to this side of the resistor, and this is connected to this side of the resistor. So this V here measures the voltage across big R. Measures V across R, right? So this can be substituted with V. So the EMF is equal to that, IIR, right? So plus. Now finally, I'm going to put this onto the other side. So I'm going to rewrite that as the V. The V is equal to the EMF minus IR. So if we compare that, to an IV graph, right? So V is Y. I'm going to use green, okay? So V is Y, R is the X, right? This negative I is equal to the gradient, right? And then this is the y-intersect B. So again, M is the slope or in the slope or the gradient, and then B is the y-intercept. Okay, so that means if you have this is your y-intercept, your B is equal to the EMF. Okay, and then here the slope is equal to negative I. Sorry, negative R. Okay, yeah, small r. So I'm gonna redo this real quick. So I'm gonna rewrite that as minus Ri. Okay, so the I is the X, the negative R is the negative M. Okay, so so that's how it's derived. It's basically from the fact that when you measure the voltage across the battery, it's the same as measuring the voltage across the resistor, the external resistor. Okay, all right. So hold on, let me redo that again. Something's really changing all my settings right now. I gotta troubleshoot this later. You know where I'm hearing from? I'm hearing you from my writing tablet. Okay, now I'm hearing you from the headphones. Let's see if that's gonna work. Can you? Okay. All right, let's continue. Um, Speakers. Ah, I see. All right, looks good. Okay, let's continue. So that's the idea. Let's put the problem in. I have a paper up here. Let's take a look at. Okay, here. Okay, so first of all, circuits. So this is the first question. Okay, so state what is meant first by an ideal voltmeter. Have you done this question yet? I don't think so. It's just that I've done this with my students before, and I don't remember whether I've done it with you or not.
No, we haven't done it.
Okay, right. Let's put this on the next one. Okay, so first of all, what's an ideal ammeter? Ideal voltmeter.
Um, is it where uh, is the voltmeter at the ideal spot right now?
Yes, it is. Now, okay, let me just discuss this briefly. An ammeter is always connected in series with the component. Okay,
A
our
voltmeter is parallel or what?
and voltmeter is always parallel. This is our component, right?
Mhm.
Whatever that is, series with component, right? A voltmeter will always be in parallel, as you said. So this is currently correct.
Mm.
Parallel to component. Okay. So this is already in its ideal spot, but that doesn't make it an ideal ammeter. Okay. Okay, I'm
So
gonna
the
ask you some.
ammeter is in series.
Sorry, say that again.
Is the ammeter in series
It
right
is.
now? Yes.
It is because look, if this is our battery. It just goes through that, right? It's in series. So with this particular configuration, you see that the ammeter connects straight with the component in series. But our voltmeter, this is our component, it connects across the component, so it's in parallel. Okay. However, I want to ask you something. This should help you remember this because a lot of people don't understand why that's the case. The idea is always for any measuring instrument, no matter what instrument it is, like it's a ruler, a voltmeter or ammeter, a spectroscope, whatever, right? The instrument must affect what it's measuring in the smallest possible way. So keep that idea. Ideally, any measuring instrument should not affect what it's measuring, right? So, why am I saying this? Let's measure. This is the case is like this because if you think about it this way, going back to the ammeter, the current has to flow through the ammeter, right? Now imagine
Yes.
the ammeter wasn't there. That means the current, all of the current must flow through here. But if you have an ammeter here, you want that ammeter to have zero resistance. Otherwise, it's going to change the current, right? So that's the idea. Zero resistance, ideally, zero resistance. So that the current doesn't change, right? Now, similarly, but it's a similar idea. You don't want the current in the component to change. So any current flowing through the ammeter must go through the component and nothing must go to the voltmeter, right? So ideally, the voltmeter must have infinite resistance. So that infinite resistance. So you already have your answer here. Okay, it's only saying state y, it doesn't actually say explain. So what's the best answer here? An ideal voltmeter. What are the properties of an ideal voltmeter? Just by looking at what I wrote here. Okay,
Hmm.
again, ideally, you want the current to flow through the component and nothing goes some elsewhere, right? And you want that current to
Like
stay the
not
same.
through the voltmeter.
Nothing should go through the voltmeter. No current should go through the voltmeter.
Hmm.
That's why we
Doesn't the
said,
voltmeter like zap like something every like one little thing?
no, it actually doesn't. Because in reality, ammeters are designed to have very high resistances, like in the mega ohm range.
Where ammeters have high resistance.
No, ammeters have zero resistance.
Okay.
Okay.
Yeah.
Now, again, ideal ammeters have zero resistance. Why? Because if this had a resistance, what happens to the current flowing through the
Then its
component?
current changes.
Decreases, right?
Mhm.
So, okay, let's go back to the question here. We're looking at the ideal voltmeter. What's the best answer you can say here? The answer's right here on this page. An ideal voltmeter should have what kind of resistance?
Hmm.
Okay, so again, you only have two possible answers. Is it zero or infinite resistance for an ideal voltmeter? You just have to choose between the two.
Yeah. Okay. Sorry. Why should a voltmeter have infinite resistance?
Because again, go back here. Okay,
Resistance.
All
Oh,
right.
does it affect the current?
We don't want the current through the component to be affected, right?
Yeah,
So go back here. The ammeter should have zero resistance because otherwise it would add to the resistance, it would decrease the current, right? If the voltmeter had low resistance, what's going to happen to the current here? Some of it's going to go there,
it's
some
gonna
of it's going
flow
to
through
go
the
there. Some of
voltmeter
them, yeah, some of
and
them.
short circuit.
If it's low enough, yes, it's going to short circuit, right? But if that resistance of the voltmeter was really high, most of it would go through the component. A little bit would flow with it. So if it had an infinite resistance, where would the current flow? All through the component. Okay. All right. So again, back to the question: what is meant by an ideal voltmeter? Let's just state that here. How would you answer that? Okay. In this case, you don't really have to. You don't really have to. Let's see. Okay. You don't really have to change any answer here. It's exactly what you have or what you can see here. When you ask to state what it is, all you have to say is has infinite resistance, and that's your answer. Okay. All right. So let's go to number two, part B, the first one. So you have the graph here. Okay. So the first question is
Hmm.
again. So we've just discussed this earlier. The first question.
This is internal resistance.
This has internal. This is already with an internal resistance, right? So the first question is. This is 1 mark. What's the EMF of the cell?
EMF. Okay.
Just remember that EMF is basically voltage, right?
Mm-hmm.
Okay. And the second question is what's the internal resistance of the cell?
Okay. I think internal resistance is easier to find.
Mm-hmm. How do you
So
find it? Actually, for
I'll
me,
start that.
EMF is easier to find.
Oh, I don't need the formula booklet, right?
In this case, no, you don't.
Okay.
Okay,
Um,
let me go back just to help
could
you
it
out.
be 8.2? Okay.
It's gonna be this, okay? It's this bit.
Yeah.
Okay.
So it's like, yeah.
All right. So with the EMF and the voltage, why do I say that the EMF is easier? Even the mark scheme actually says it's
So
easier because this is 1 mark.
8.5.
Yeah. 8.5. All right. And how about the internal resistance? This is 2 marks.
Um, is it V equals IR? Is it like what's the equation?
Again, let's go back.
Uh,
Y-intercept
oh, V over I.
and slope, right?
So it's 8.5 over like 5.
Mm-hmm.
No.
Not quite. Remember, how do you find slopes?
8.5.
You don't use a single point for slopes. You use 2 points.
Okay, so 8.50
Mm-hmm.
and um
And
I'll use a better point.
you can always pick the real
5.8. 5.8 over 4.2.
4.2, this point, right?
Yes.
Okay. Not quite. You reverse them. Remember, x-axis first, right?
Oh no, so I was putting them as a fraction. Sorry, my
Okay.
bad.
All right. In that case, yeah, that should be fine then. So, if you do it like that, this is 8.50 like that. Then minus this one. You said this was 4.2, and then what was this?
5.8.
5.8. Okay. Uh,
No, it's not.
it is.
Wait.
This part is correct. However, I doubt that this is 8.5. That looks like 9 to me,
Yeah, it looks
right?
like 9.
Yeah, that should be 9. Okay. Calculate that. So that's now correct. This is 9 volts. So
I think it's
9.0.
5.4.
Hmm? Sorry. Okay, let's calculate that real quick. Okay. So that's gonna be 9 minus 5.8 divided by 4.2. It gives us 0.76 but negative, right? Okay, negative of this. So that would be 0.76 ohms. I got 0.76 ohms. So this is correct. Okay. All right. So again, to find the internal resistance, just find the slope and then turn it into the negative value. It's already going to be negative, so turn it to the positive value instead. Yeah. Okay.
Mm-hmm.
All right. Let's go to C. This is now about drift velocity. Before we go there, a recap. Okay. So drift velocity. The equation is I is equal to N Q A V. Okay. What's this? It's a current. N is charge density. Okay, usually given in electrons per cubic meter. Okay, electrons per cubic meter. Okay, Q is the charge. This is normally charge of particle, the carrier. Okay, so normally an electron. Okay, A is the cross sectional area of the wire. And then finally, what's V? V is the drift velocity. Okay. All right. So with this, uh, let's take a look at the next question. The next question is, I haven't copied this. Okay. So you have a wire in a circuit. The dimensions are given. Bless you.
Thank you.
All right. So here, you have a wire. The dimensions are given. The current is given. The charge, the number of electrons per unit volume is given, and show that the drift velocity is that. Now, another clue here is when you say show, you must give your answer. Okay, give the answer to three or more significant figures. Okay,
Is this one 2 sig figs though?
yeah, this is two sig figs, right? That's two sig figs. So when you say show, your final answer must have three or more sig figs because the idea,
Oh.
okay, because of the command term show.
Mm-hmm.
Okay, it's basically calculate, but you have to really show that the value is close to what's being given to you, close to it.
Right.
Okay. All right.
Um.
So, okay, this is in the formula booklet, so I can let you just look at the formula here. This is the exact same formula in the booklet.
Right.
Okay.
Okay.
All
Got
right.
it. Okay.
All right. Uh, okay. So, how do you? So again, you start with I equals uh,
NAVQ.
NAVQ. we're looking for V, right? So from here we get
Yeah.
V is equal to I over N A Q, right?
Yeah.
Our I is given 2.5. Our charge density N is given. What's the charge density? That's that.
Oh, 2.4 times 10 to the 28.
10 to
Is
the
that
20.
that's n
That's 28 per cubic meter.
times pi times r
Okay.
squared?
Pi times our R. The radius is 1.2 millimeters, but we have to change that into meters. So 1.2 times 10 to the minus 3, because it's in millimeters, right? Then you square that. And then finally, Q is charge of the electron. Charge of the electron is given in the data booklet, so I'll just give this to you. 1.6 times 10 to the minus 19 coulombs. Okay?
Yes, I got 2.01 times 10 to the negative 4.
Okay, yep. Alright, so you got the final answer of
Yeah.
2.01 times 10 to the minus 4, which is exactly what we want, right?
Hmm.
Meters per second. Shown. Okay, so again, when you see show, always give like one or more decimal places or one or more significant figures than the previous one. Okay, all right, next. Okay, this time this is about magnetic fields, still related to that same question though. So here's the question. Okay, so the diagram shows this cross-sectional view of the connecting wire in C. So there's the cross section, there's the magnetic field, and then the current is into the page. So the wire which carries the current into the page is placed in the uniform magnetic field of flux density 0.5 T Teslas. Okay. To determine the magnitude and direction of the magnetic force on one of the charge carriers on the wire. So you have to think about this. In a wire, in a metal, the charge carrier is automatically a what? What's this first? So it's a wire, it's metal, so this should be an electron. So keep that in mind when you solve this. Okay. So what do you have here then? You have here a wire with a current. You have here a magnetic field, and you're trying to see which way the charges are going to move. So which hand rule do we use here?
Which handle?
Hand rule. Is it the right hand rule or the left hand rule?
Right hand.
Right hand. How do we use right hand here?
I don't really know.
Okay, so let's go to the hand rules. Okay, let's recap that. Hand rules. Okay, now first of all, there are two right hand rules. This is by the way, this goes for magnetic fields. Okay, and motion. Okay, so first, your right hand rule, there are two. Okay, both of these are grip rules. Okay, first is for us for straight wire. Okay, straight wire, and then the second one's for a coil or a solenoid. Okay, now the other one is the left hand rule. It's gonna be better if I show it to you, but for now I'm just gonna write this here first for us to uh, see. Okay, now the left hand is not a grip rule. Okay, it's more of a pointing rule. Okay, so this is gonna be for this also. Actually, no, it's the same. Okay, this works for both currents and for velocity of a charge. Okay, so the best way for me to do this is first I'm gonna show you a straight conductor. Okay, I am going to use, what will I use for my straight conductor? Okay, I'm gonna use my pair of scissors right here. Okay, so let me go back to the normal board. Okay, all right. Oh, by the way, my lights are not properly working. Everything's going wrong today. So yeah, if you don't see me clearly, that's the reason. It's if I look dark.
It's okay.
All right, but anyway, you can still see the scissors, right?
Yeah.
So imagine that the current on the scissors is going up. Okay, so the first grip rule is for the straight wire. You grip your wire so that you're well. It's obvious that this is the only way you can grip your wire, right?
Yeah.
Okay. Now the thumb should point in the current's direction, not the electron flow direction, but the current direction. Okay. So of course, if the current's flowing up, the electrons must be moving down, right? So you have to use the conventional current, so going up in this case. The thumb points in the current, and you see how my fingers wrap around the scissors. That's how the magnetic field would look like. So if I do it like this, it's a bit easier to see like this. Again, thumb in the direction of the current. And then if you look here, it looks like from your point of view, it kind of looks like my fingers are wrapping counterclockwise, right?
Hmm.
So this means when you draw this, the current is going, from your point of view, the current's going out of the page, right? Current's
Yeah.
going out of the page, and then the magnetic field is going to wrap around it in a counterclockwise direction.
Wait. So
Similarly,
is this current?
yeah.
If you're using the right hand, is this current?
No, no, no. For the right hand, that's different. That's You should use the left hand with that.
Oh, for current.
For left hand, you do what you're doing. But for the right hand, think about it this way: most people are right-handed, and most people would grab stuff with their right hand.
I'm left-handed though.
Yeah, you're left-handed. Okay. Yeah, I
Oh.
could. Yeah, but think about it. It's just most people. Okay, so when most people do it, right hand. Yeah,
Oh, this is the direction of the
magnetic field. Okay.
field.
Yeah.
Isn't this I?
No, no. This is I for straight conductor. Okay, so
Oh, I
let me just
field.
write that down here and go back to the
Is this a
board real.
solenoid? Or am
The
I now
solenoid,
I'm tripping it?
the one you're describing now is actually for the solenoid.
Yeah, because it's like this, but it goes
Yeah.
this way.
So thumb in this case, straight
But
wire
if it was going
thumb.
that way, it would be reversed.
Okay. Okay. Thumb is current, and then fingers fingers would be magnetic field, right? For the solenoid, it's the other way around, as you said. The thumb points to north, right? Okay, and then the fingers follow current. Okay.
Hmm.
Okay. So here's an example. I actually have a spring here. I'm gonna go back here real quick. Okay. Hope you can see this. Okay. So in the
I see
spring,
it.
okay, you see the spring. Let's say
Yeah.
that the current is flowing this way, right? So going around this way. So same thing. I'm gonna grab the wire, but this time the fingers flow in the direction of the current. So in that case, the north pole is gonna be here. Okay, the thumb points to the north pole. Similarly, if the current is going the other way, like that, so finger like this, north pole is here, to my right, to your left. Okay,
Hmm.
so similarly, it's just like that. Now for the left hand rule, the one you were pointing to, this is three things. Okay, um, for the left hand rule, let's go back to the board. for the left-hand rule, basically think of it this way. You have three objects, three quantities that are perpendicular to each other. Okay, so we have that, that, and that. Um, this is gonna be force. This is gonna be your B. This is gonna be your I. This is gonna be your thumb. The index finger would be the I would be the middle finger, and B would be index. Okay. Again, F for force, B for magnetic field, I is for current or velocity.
Mhm.
Okay, so let's read. Okay, so just a quick one before we continue. So with my left hand, force, force, magnetic field, current. Okay. Um. Okay. So let's continue. Let's go back to that question. So determine the magnitude and direction. Oh, one more thing. Did we do magnitude yet? Not yet. So this is in the data booklet, but I'll just write it here. The force, the magnetic force will be equal to either BIL uh, or BQV, depending on whether you have a single force or whether you're talking about a single charge or the entire current. Okay, there's a sine theta here, but most of the time, we ignore sine theta. Okay, because most of the time our directions are, or rather our angles between BI and L are all 90 degrees.
Mhm.
All right. Okay. So again, these are usually ignored. Basically, once they're all at right angles, just do this. BIL or BQV. Okay. What's I? That's the current through the wire. So I'll just write that. That's current. L will be length of wire. Q would be the charge of the particle. And V would be the velocity of the particle. Okay. So I'm gonna make that V smaller, just like that. Okay. All right. So which one do we use here? For magnitude, you use the formulas. For direction, you use the hand rules. So you're given the current, and you're given the magnetic flux density. Okay. We know that this current from before is the same as this particular current, right, in C. So that should be a useful idea for us to get the final answer.
Um, B is magnetic field, right?
Yes, B
Field
is the
strength.
magnetic field.
Is this connected to the right hand?
It it's connected to the right hand question, but you don't use the right hand rule yet. Use the left hand.
For this? Okay.
Mm-hmm.
Right. Okay.
Okay.
By the way, your screen's not sharing.
Oh, right,
I'm just looking at this.
right, right. Sorry. There we go.
Thank you. Oh, okay, okay. So looking at the Jamboard, why the um okay, magnetic field. So B is 0.25.
Correct. So let's label this. This is your B. Now, okay, what else is given? Remember that this problem is identical to the problem in C, which means you could use something here in C. Which one is,
Hmm.
what's the useful thing you can get here?
Is L length? If L
Uh-huh.
is length,
Yeah, but are you
then
actually given the
you
length
use
of the wire? You're not, right?
you're not, yeah.
So, in other words, going back to these two formulas, you can't really use this. You have to use this, right?
Mm-hmm.
So, since you have to use the
Q, the
BQ,
charge electron.
Yes.
Negative 1.6 times 10 to the negative 19.
So Q, let's write that down. 1.6 times 10 to the minus 19, correct? And then,
Positive or negative? Negative?
well, in this case, it doesn't matter yet, but it should
Okay.
be negative. Let's just put that in there.
BQV.
Okay, so you need a
V, we
V.
don't.
Yes, you do, because it says so right here.
Connecting wire. Oh, okay.
So we have to go back to
Oh,
C.
so it's on the previous page. V is 2 times 10 to the negative 4.
All right, great. So V equals 2.0 times 10 to the minus 4. All right. Now, can we solve for the
Yes.
magnitude? Yes, we can, right?
So I'll put that in the calc now.
All right, great.
I got 8 negative 8 times
Mm-hmm.
10 to the negative 24, and the direction is left.
Okay. So the correct. Okay, let's just do that quick. Calculator. That's going to be 1.6 exponent negative 19. Whoops. 1.6 exponent negative 19 times b, which is 0.25, times v, which is 2, times 10 to the minus 4. So you're right that it should be 8 times 10 to the negative 24. Correct. So F is equal to 8.0 times 10 to the minus 24 newtons. But the direction is not correct. So you got 1 mark. Okay. So if I'm going to draw this like so, uh, remember that the current is going in. Current is going in, right?
In
Into the page. So that's
um
gonna be your middle finger, pointing into the page, right? Magnetic field is given, it's pointing to the right.
right.
So the force
Is
on
what
the
to the right.
carry on the force on a positive charge would be going down. But the electron,
Yeah.
as you mentioned, is negatively charged. So that means the force on the electron is going to be the opposite direction. So up on page. So the answer here is up on page. So in other words, if you draw it, that's the answer.
Wait, so what's the original direction?
The original direction of down. I'm gonna use yellow here. Okay, so this
Is
force.
original out of the page?
No. I would think of it like this. Okay, the original here is still into the page. The current is into the page.
Yes.
Okay, but the question is, the charge carrier in a wire is an electron, so that means the electrons. Okay, so that should mean that the electrons move out of the page. Okay, now for me, I don't normally think of it like that first. I usually do the changing at the end. I usually stick with this because it's easier to do the hand rules with that. Okay, so the current here is into the page. So if you use your right hand rule, so again, I'm going to use it from your point of view. B is to the right. Okay, magnetic field is to the right, and then current is into the page. So like that. All right. And what do you
Yeah.
okay? So you see that the force is pointing downwards. So this is going to be the
Really?
force on the current. On
Wait,
the current.
how's the voice pointing downwards if the current's into the page?
Yeah, hold on. Yeah, because again, oh, am I pointing? I think I'm pointing wrong in your direction. So into the page is to me, right? Okay, so let's do that again. So magnetic field is here to the right. Then current is, okay, B is to the right, current is to me. So it looks like this. So my thumb is pointing to me, at pointing down, right?
Wait, what? If your current is
Okay, I'll do it
pointing
from
to
my point of
you,
view first. It's a bit hard with the twisting. From my point of view, it's into the page. Current is into the page. Magnetic field's to my right. So the force points down. So this is the force on the positive charge.
is
So
pointing
the force
down
on the
towards
negative charge
you.
would be the opposite way.
What does force pointing down mean? Does it mean like
Does that make
to
sense?
you? Because like
So
this
let
is
me write
what
that
I have.
again. So just so we're clear.
Because
Okay.
I can't really see your hand.
So on a positive charge, okay, I into page, right? Then B to right. So this means these two together, the force must be downwards.
But if current is downwards,
So
how
from
is
here,
force also down?
negative charge experiences opposite force. Or in other words, an upward force. Okay, so does that clarify the direction? I think for the magnitude, we're okay. Just use the formula and done, right?
Wait. If you said
But do you have
current is
any
into the
questions on
page,
the direction? Does that make
you
sense
said
to you now?
current is into the page down.
You're still trying to figure it out, aren't you?
Yeah. Wait, can you hear me?
Hold on. I cannot hear you. Hold on. I think it's me. Try that again.
Hello?
Yeah.
Okay. So you said current is down, which is into the page. So how's force down if it's pointing at you?
Okay. Because by down, oh, because it's your point of view. From my point of view, into the page is horizontal because I'm looking at a screen, right? So, okay, let me do what I mean. Let me show you what I mean here. If we draw that again, current is that way, right? So if you look at it down, if you look at it on the table, this is into page, right?
Yeah.
Okay. Don't think of down as an actual down. Think of this as this is left, right? So this is gonna be right. That's gonna be left. This is gonna be out, right? So what's this gonna be? It's gonna be up and down here and up. As in you're literally going down the page. You're moving across the
Oh,
page, you go down it, right?
yeah.
All right. I think that just gave you a big headache. I think.
No, I'm just sick. I'm sick
You're
today.
still sick. Still sick. Or is this something new?
I'm just like sick, like sore throat and like headache.
I think the stress is getting to you for these summatives and everything. Your mocks are also coming
Oh
up
yeah.
soon, right?
My mocks, yeah. How do you know I have like three summatives this week?
You you kind of told me that you have a summative. I don't recall you telling me it's three. You did tell me though that you're gonna have some summatives.
Yeah, I had like physics, Chinese, and math this week. Oh,
Yeah.
and my TOK essays due, like
Oh,
final draft
TOK essay. Also, how about your EE done?
done.
Good. Right. So okay, we'll end it here for now. I think I don't want to cause you a headache. Well, a worse one
Mhm.
right now. So we'll end
But
here.
I think I understand that. You
Yeah.
say down as in down the page. This
Yeah.
is going into paper.
Yes. Yes. That's
So the
right.
directions are just this and this.
Uh-huh. That's right. So just
Okay.
always remember up, down, left, right, in, out. Okay.
Yeah, but current, well, can current ever be like this way?
Yeah, it can. So how would that look like? I just want to finish that. So for example, that's your wire. That's your I, right? Going that way. And then let's say that my magnetic field is gonna be pointing this way. So which way is the force?
Oh, the force is going. What's this way?
Is that out or
Out.
in? That's out. Okay,
Out.
so force will be out.
Okay.
Okay. So it is possible, but most of the problems you will get is either B is it's either this would be B, or these would be I. You rarely see a problem that looks like this is rare. Okay. I don't know why they don't put this two a lot, but it's usually these two that you see.
Okay.
All right. Okay. All right. So we'll end it here. Just take a rest.
Okay.
Take a
Thank you,
breather.
Mr. Dan.
Literally take a breather. Okay.
Yeah.
All right. I'll see you next time on Thursday. Okay.
Okay.
All
See you,
right. See
Mr.
ya.
Dennis.
Bye bye now.
Bye.
Okay. So regarding the stream, hi everyone. Sorry I wasn't able to talk to you. I I got home. Well, it's a Sunday, so it's a Sunday, and I am a Christian, so that means I go to church on Sundays, and you know what that means when you have a little kid in tow. You don't go home straight away. So that's normally why on Sundays I don't get to set up earlier than what I want to do, and I just usually go straight to the stream on Sundays. So I guess okay, we'll end it here because nobody's here, I think, unless somebody's there. If you are there, say hi. All right, but anyway, like I said earlier when I was talking to CJ, again, a lot of things went wrong. It actually started going wrong yesterday. Like I couldn't set up my sound properly, and now one of my lights is dead. I gotta get a new set of lights, I guess. Well, with that though, it doesn't really matter as long as you get to learn something. That should be okay. All right. So again, just want to do this real quick. If you haven't done so yet, please follow us and subscribe and like us on YouTube, Facebook, on Freaky Physics on Instagram as well, and in TikTok. And then our backup stream is on Twitch. So yeah, I wasn't speaking of which, I wasn't even able to change the video settings to the stream. So you may see something like math right now. So yeah, that's how hectic it is today. And then with all the things going wrong, so like I said, I do apologize for that since yesterday actually. So with that, I'll end the stream here. So hope you learned something. Stay freaky, everyone. Bye bye now.